Okay, so we are starting off our chemistry unit now, and we're beginning with section 2.2, part 1. So you'll notice that everything in the biology unit was 1 point something. The chemistry unit is always 2 point something because we're in the second unit. So we'll be starting with section 2.2 as 2.1 is safety, which we already covered. And then 2.2 is going to be broken into a total of 6 parts. So here's an overview for our unit. A couple of these concepts are review, a couple of these things we're going to be working through, and then some of it will be based on how much time we have for the course. So the structure of atoms and molecules and naming compounds and writing formula. This is review from grade 9. Rearrangement of atoms in chemical reactions, energy transformations in chemical reactions, acid-base chemistry, and nuclear energy and decay are all new. However, we're likely only going to be getting through these 3 due to time. So we'll see we may get to nuclear energy and decay, which is radiation, but due to the speed of the quarter system and how much we have to get through, we may not make it to that. So we're kind of covering the things that are necessary to prepare you for next year. Okay, here's an overview of the key concepts, which you should have already started from yesterday, and the key terminology. Okay, again, we watched this video yesterday, but if you do want to rewatch it, feel free to copy the link. It is Crash Course. If you haven't watched it, then you definitely should, and then make sure you're staying on top of your lessons each day. So this is a rough timeline for the history of the atom. So the theory of an atom dates back to 460 BC, which means 400 years before zero. We are currently 2021 years past zero. And then Dalton in 1803, so just over 200 years ago, came up with a little bit more to emphasize this. So not a lot changed in 100 years, but after that there was a bunch of discoveries and theories relatively close together. So Thomson in 1987, Rutherford in 1912, Bohr in 1913, and then in 1930, there were a bunch of contributors to the modern quantum cloud model, which is basically what we are currently working with in today's time. So page 94 of your notes gives you an overview of their discoveries in a timeline. So please make sure you pause this and copy down and write down the names if you haven't. In this course, we're essentially going to be working with the Bohr model. So we'll be looking at a simplified version of the Bohr model, and we'll treat things almost the same way as you did last year with Bohr models. Okay, so atomic theory and bonding. An atom is the smallest particle of an element that still has properties of that element. So what that means is that you can take oxygen, for example, and talk about the properties, i.e. things like melting point, boiling point, color. And so one single atom of that oxygen is the smallest thing that will have those properties of oxygen that you know of. Atoms are really, really, really small. So 50 million atoms lined up end to end would be about 1 centimeter in length. Atoms are made up of subatomic particles, so protons, neutrons, and electrons. And subatomic particles on their own do not have the properties of an element. Atoms join together to form molecules. A molecule can be an element or compound. And a compound is a pure substance that is composed of 2 or more atoms combined in a specific way. So if we combine atoms of the element oxygen with atoms of the element hydrogen, you get H2O, which is a compound. So 2 elements of oxygen and hydrogen as a compound give you water, H2O. It's an element when you only have one type of atom present, and a compound when there's more than one type of element present. Okay, so what are each of the following? So take a moment and see if you can figure out what each of these images is showing us. The terms you're working with are on the right side, over here. So atom, molecule, compound, and mixture. So this should be review from Science 8, so you can use the terms also in more than one picture. So I'll give you a second and then we'll go through these together. First off, a single atom. Then we have a molecule as well as a compound for this one. So you can see that there's multiple atoms present, bound together to form a compound. Molecule as well as a compound. Molecule. This is an example of a compound, so you have multiple molecules present. And a mixture. So in order to talk about chemistry, we have to talk about chemical changes. So this is going back to grade 8 again. A chemical change occurs when the arrangement of atoms in a compound changes to form new compounds. These are non-reversible and make a new product. So your end result is different from what you started with, and you can't really go back to the original, i.e. you can't uncook an egg, you can't unrust a nail. You can only remove the rust, but you can't turn the rust back into a shiny nail. And then there's a few other examples there. Okay, so atoms are made up of smaller particles called subatomic particles. This is what we just talked about. Again, I'll review. So subatomic because it's smaller than an atom. So I'll pause here for a second so that you can get all this information copied down. So the table shows the three main types of subatomic particles. So for example, we have a proton, which we symbolize with the lowercase letter p. It has an electric charge of +1, or 1 plus. It's located in the nucleus, and it cannot leave the nucleus. It has a relative mass of 1,836. We will get back to that in a second. So a neutron, symbolized by lowercase n, has an electric charge of 0. It is also located in the nucleus and has a relative mass of 1,837. An electron, symbolized by the lowercase letter e, has an electric charge of -1 or 1 minus. It surrounds the nucleus, as shown in the atom diagram off to the right there, and it has a relative mass of 1. So to go into relative mass in a little bit more detail, what this means is our electron is the smallest, and protons have a mass 1,836 times greater than that of an electron. And the neutron's mass is 1,837 times greater than the mass of the electron. So if you took a proton and an electron together, their combined mass would equal that of a neutron. And their combined charge would also be the same charge as a neutron. And then the diagram just gives you an overall structure showing neutrons and protons in the nucleus, all kind of tightly together. And then the electrons are in rings surrounding that in red. Okay, so the nucleus is at the center of the atom. The nucleus is composed of protons and neutrons. Electrons exist in the space surrounding the nucleus. The number of protons equals the number of electrons in every atom. So this is the key word here. It's not an atom. This is not true. So protons do not always equal number of electrons. Think back to ions in Science 9. But if it's an atom, then it is all the time. So protons cannot equal electrons in an ion, but they will always equal each other if you're referring to an atom. Nuclear charge is the total charge on the nucleus due to the protons. So it's the same value as the atomic number. So as long as you were talking about an atom, the atomic number will equal the protons, which will therefore equal the electrons. But if it's not, then the atomic number will only equal the number of protons. So that is this point here. Atomic number equals number of protons, and in an atom, number of electrons. Atomic mass, average number of protons plus neutrons. So the atomic mass is found on the periodic table as well, just like the atomic number. It is important that we distinguish that this value is an average. So just like in our image here, the atomic mass is shown as a decimal. So you will generally find this as a decimal value on the periodic table. This does not mean that there is part of a proton or neutron. It means that you're averaging those values out. So a few examples to try to practice reading the periodic table. So for example, based on the images provided here, this is really the main thing to notice on that one. Other than that, they're essentially the same picture. But what is the atomic number of this? What is the average atomic mass of this? What element is this, etc. So answering all of these questions. And worthy to note, for the ion charge, anytime you see a -1, or sorry, a negative, it means -1. So negative, a -1 charge. If you just see a plus symbol, it means +1. So we just don't write the ones in, but it is referring to a 1. Okay, and for this next slide, again, you might want to pause. This should be in your notes, but complete the table for different ions. So for the first two, they have been completed to help you through. So I'm going to talk you through a couple of the examples, pointing out a few things. So remember that our atomic number is equal to the number of protons. So this is always true. This doesn't change. As you can see here, same for phosphorus. Same. How we get the number of electrons, though, is based on the ion charge. So if it has an overall 1 plus charge, that means that there's more of a positive charge than there is a negative charge. So there's essentially less electrons than protons. So 18 is 1 less than 19, giving it an overall 1 plus charge. The number of neutrons is based on the atomic mass. So the mass for potassium is 39.1 from the periodic table. And in order to get neutrons, we take the mass minus the atomic number. And the reason we do that is because protons plus neutrons equals mass. So if we take protons away from mass, then you end up with just the number of neutrons. So, and to check this, we would go 19 plus 20 neutrons gives us our mass of 39. Again, remembering that that 0.1 is just because of an average, so we round it to the whole number. This +1 also tells us we have an ion, where for phosphorus, we're dealing with an atom. So if you see a 0 ion charge, you're dealing with an atom. And in this case, we can see that the number of protons is equal to the number of electrons, which is true for an atom, but not an ion. If you have the atomic number, which is the same as the number of protons, you can figure out the element name. If you have the element name, you can figure out the atomic number off of the periodic table, and then figure out the number of protons, and so on. So let's quickly look at how we got this 1 plus charge on potassium. So potassium is symbolized by the letter K on the periodic table. Based on its atomic number, it has 19 protons. From the table, we were told it has 18 electrons. So we're dealing with an ion. We have 19 protons, which have a each have a +1 charge, giving us a value of positive 19. And we have 18 electrons that have a -1 charge, negative charge. So minus 18. So you're adding integers here. We have a +1 net charge. So overall, the ion is positive. It has one more proton in comparison to electrons. And remembering that in a particular element, the proton number can never ever change, only the electron number can. And this is because the protons are tightly in the nucleus where the electrons are circulating, and they can be lost or gained or shared when they form compounds. For phosphorus, it has 15 protons. So 15 times each proton has a +1 charge. And because we're dealing with the atom, it has 15 electrons, which each have a -1 or a -1 charge. So we've got +15 for the protons, -15 for the electrons. Add these together, you have a 0 net charge for an atom. Okay, so before you move on to the next video, please pause here and make sure you are capable of answering these questions. If you can answer all of these, you are ready to move on to the next video. If you can't, then you need to go back and review the video, make sure you're clear on everything, and then you can move on. So this is the end of section 2.2, part 1.